Good day. Today's tutorial will be presented by
Nathan Gallon,
and myself, Jean-Michel Fried, and will involve free open source Field Programmable Gate Array FPGA development frameworks for radio frequency communications.
This tutorial will hence focus on design and realization of a software-defined radio SDR transmitter. Now, as a quick reminder of what is the reason for radio frequency communication, we wish to convey information from one speaker to the other speaker. Now, in order to share the spectrum and to have antenna dimensions much smaller than the baseband signal, here this information is centered on 0 Hz, we transpose this information on an intermediate radio frequency carrier that will allow us to share the spectrum between multiple users. Now, this intermediate step of implementing the information over the radio frequency wave is called modulation. So this modulation step here will both imprint on one of the 3 quantities that is representative of a radio frequency wave. So we have something of a shape amplitude times periodic signal and a phase, and all these quantity can carry the information in terms of amplitude modulation, in terms of frequency modulation, or phase modulation. Now, the resulting communication will be received by the receiver here, and the objective is to remove this intermediate radio frequency carrier to recover the information that was transmitted. And this means that we will need in the FPGA to generate the information and this radio frequency carrier. This will be several megahertz bandwidth. This will be several tens to 100 megahertz carrier sine wave with its modulation scheme. And generating this multi-megahertz bandwidth and tens to 100 megahertz carrier is well beyond the capability of general purpose central processing unit CPU. Hence, the need to understand and master the details of field programmable gate arrays, a matrix of reconfigurable logic gates that will be able to handle all these tasks of modulating information over radio frequency carrier. Now, if we were to work only with real quantities, we would have an even spectrum and we would be wasting half of our bandwidth. Indeed, if you look at the radio frequency spectrum of a discrete signal, it will be going from minus half the sampling rate to plus half, so that would be half your sampling rate or Nyquist frequency. This will be plus half your Nyquist sampling rate or Nyquist frequency, and the modulus of a real valued quantity is an even spectrum. And that means that we duplicate the information between the negative and the positive part of a spectrum, and naturally this waste of bandwidth is inefficient. So naturally, with software-defined radio, if we wish to create an asymmetric spectrum, like a positive part that is not the symmetric of a negative part, we will have to replace this real quantity with a complex number. And by doing this, we create both quantities in phase and quadrature. So this exponential of j omega t being equal to cosine of omega t plus an imaginary part j sine of omega t, and this real and imaginary part will naturally express the kind of signal that is going to be transmitted using software-defined radio. So in our implementation, we will create a complex number exponential of j omega t local oscillator, and this is the quantity that will be generated by the FPGA. Finally, in order to make this tutorial as widespread as possible, we will just be using a general purpose input-output pin as oscillator output, meaning we will not be programming D2A converter, digital to analog converter, but we will just be toggling a GPIO for transmitting the signal. Of course, this means that we will have an awful spectrum with a lot of harmonics, a lot of unwanted spectral components that should never be transmitted over the air. And in our case, we will be testing the validity of our signals by using a wired configuration between transmitter and receiver, of course putting enough attenuation here not to damage the radio frequency front end of our receiver. So this general outline of radio frequency communication tells us how we're going to address this tutorial. So some of the requirements that have defined our selection of tools is to try to be as independent of a given vendor so that our work will be valid on any FPGA, any vendor, any brand. So that's one of the objectives. We want to avoid dependence with a given framework. Also because we would like to try to have as fast synthesis as possible when you synthesize a full RF NOC framework, for example, for Etus Research high-grade SDR radio frequency devices, you will have multiple hour synthesis duration. In our case, we would like our setup to be able to synthesize in a few minutes, so we have a fast turnover and be able to test multiple ideas. Finally, we would like to try to get rid of some of the historical hardware description language, such as Verilog, VHDL, which are quite verbose, and try to benefit some of the modern functionality, especially of Python programming, and this is provided formerly in MyGen, now called Amaranth. So this is the language that we have selected for developing our software-defined radio transmitter. This demonstration will focus on the Zinc 7020 fitted on the Z board, but of course you are more than welcome to try this on any other FPGA, as will be demonstrated by Gwen at the end of this tutorial. So just to remind you what will be our objective, we will first generate a baseband signal. This will allow us to get started with FPGA programming, and just to try to make something reproducible and interesting, we're going to make a pseudo-random sequence generator. So this pseudo-random sequence generator is, for example, the kind of signal that is used for code division multiple access, which is the case for GPS, for example. So whenever you want to have multiple speakers that are selected or identified by their code, these linear feedback shift register are the choice of synthesizing these non-repetitive patterns. This output will be first assessed, and once we'll have checked that our LFSR is working as expected, we're going to try to address how to generate a local oscillator, and we're selecting this 70 MHz local oscillator as a trade-off between radio frequency wave transmission and something that is accessible on most FPGA. Again, this would not be transmitted over the air, and in our case, we're going to send this through a filter, a surface acoustic wave bandpass filter, to a software-defined radio receiver for assessing the quality of our signal. So that's the outline of this presentation. So let's get started first of all with this part of generating the local information. So the local information is a linear feedback shift register, and that's our baseband signal structure. So the baseband, remember, is the signal centered on 0 Hz. That is the information to be carried. And we've selected this linear feedback shift register because it will allow us either to have some ranging capability. So whenever you have a non-repetitive pattern, you will be able, through correlation, to find where this pattern is located in the noisy signal that you've received. And I'll try to discuss a little bit the benefits of this approach. And furthermore, we're going to identify which speaker has transmitted. So these are two linear feedback shift registers. So in the linear feedback shift register, this is here the shift register. So every clock cycle, the content of the register is going to be shifted to the right. And in a linear feedback shift register, we have two taps, two locations of a register which feed an XOR, exclusive OR, and the output of this XOR is sent back to the input of the linear feedback shift register. By wisely selecting the tap, so the location of these inputs here, we can demonstrate that the length of the sequence that is generated is 2 to the n-1, with n the length of a shift register. Now you might wonder how we're going to select the location of the taps. Well, there's a whole theory around it, but my approach, practical approach, is, for example, to go on this website, and here we've got all the register lengths and the number of possible linear feedback shift registers. So as you're going to longer sizes of register, you see that the number of possible combination becomes tremendous. This, if you take, for example, the case of the 7-bit long shift register, you have here the list of taps, and the taps are represented as the location where the XOR is feeding. So in this case, for example, you would say that here you have 2 to the 0, 2 to the 1, 2 to the 2, 3, 4, 5, and 6. That's the 7-bit long register. And here, 2 to the 3 over here would be 8. 2 to the 2 over here would be 4, 0, 1, 2. And so this means that you will represent this polynomial as hexadecimal 48. Similarly, here you would have 2 to the 3, 8 here, 2 to the 0, 2 to the 1, 2 to the 2. So here we have 2 plus 4 equals 6. So this would be 0x60 if we represent the polynomial. So if we wish to try to play a little bit with these polynomials, we can actually generate them in GNU Radio. So if we launch our favorite tool for prototyping radio frequency signal, and so that's GNU Radio, and if we search for linear feedback shift register, we've got the Galois field linear feedback shift register that we can create here. And this GLFSR will, if we double click, we can have a seed of initial value, never 0, because 0 is a pattern that will always repeat itself. So that's why we have 2 to the n minus 1 and not 2 to the n. 0 is forbidden. And the degree would be how many elements we have. And the mask is this polynomial. So that would be, for example, 0x60 for our linear feedback shift register. And once we've got this guy over here, we can try to display the spectrum. So if there is some repeated pattern, we'll have some spectral component. If we have truly noise, then we should have a flat spectrum, because the Fourier transform of noise will be a flat spectrum. All frequency contributions are equal. Remember, if we do only simulation using GNU Radio, we must make sure to slow down the data rate and introduce the throttle block that will prevent GNU Radio from trying to stream as many data as it can. So if we connect all these guys together, here we have our GLFSR source, and running this flowchart will indeed exhibit the spectrum of this sequence. So here we have our flat spectrum, no specific spectral component, and similarly we can check that the other component that we had was similarly with no specific spectral component, so there is no repeated pattern. Let's see how, here is an example which is a repeated pattern on purpose. So now that we're familiar with the outline of the baseband signal, let's see how Nathan can implement this with Gwen on the FPGA.
LFSR Fibonacci principle look like this scheme. We have a register, in fact a bit vector, and a series of XOR. This XOR use some specific bits of the register. The offset of these bits is fixed by the taps. The interesting aspect with this type of algorithm is to use the combinatorial and sequential concept of FPGA. For example, a XOR is combinatorial. This means the output depends only on the input signals. There is a small delay, as shown in the lower part of this chronogram. This is due to hardware and delay of propagation into wire between components. For example, here the output is updated just after the second input is updated, and again the output is updated after the first input is updated. The second concept is a sequential. The register is sequential. It's something like a sample and hold for A to D converter. In this situation, the output depends always on the input, but again on the previous value. It maintains this value until a specific signal change. This, for example, here where the output of a flip-flop is updated when the clock signal goes high, and the output become the input, here the high value. Here the output of the XOR change 2 times, but the output of the sequential part is not updated until the next clock edge. In fact, here we don't show a change in the Q signal, but it's due to the fact the output of the XOR is again high. In Amaranth context, everything is class. When an algorithm must be implemented, it's required to create a new class inherited for elaboratable. The most important method of this class is the method elaborate called by Amaranth itself. This method is used to do everything according to the algorithm. The first thing is to instantiate a new module. Module is a complex method providing some functionality or features, for example, to allow us to create new submodule, in fact, instance of another class, or to access to domain. There is a comb domain. D is for domain. The comb domain is a combinatorial part, and the sync domain is the sequential part. Sync is the default domain using a clock, but it's possible to have more than one sequential domain. Here, the second thing we do is to create a signal. Signal has the same behavior, the same ID, is the same ID as in Verilog, wire, and reg. Without parameter, this signal has a size of 1 bit. With a parameter, this second signal has a size of 2. Comb and sync are in fact a list of operations. The first, combinatorial part, is the update of the first 1-bit signal by using EQ, is equivalent to equality or affectation, and this is the operation. We use a XOR between the first and the second bit of the second signal. The second line with the sequential domain is to update the second signal by using a concatenation between the second bit of this signal appended with the output, the result of the XOR. At the end, the instance of module containing all comb, sync, submodule, etc. is returned. And at the end, Amaranth produces a tree of all modules, submodule, etc. Amaranth is based on Python class, but most of synthesized tools like Yosis or Vivado or Quartus, etc. are unable to read directly Python. It's required Verilog, VHDL, or system Verilog. So the first thing done by Amaranth is to produce a Verilog equivalent of the gate array written in Python. This Verilog is used as an input by the synthesis tools to convert some part, for example, the XOR to LUT or to specific primitive for the targeted FPGA. The result of this first step is the input of a second step, placement and routage. with tools like NextPNR, VTR, or Vivado, Quartus, etc. These tools are used to map every primitive to the FPGA structure. At the end, a bit stream is produced. This is the image of the content of the FPGA. And this bit stream is used by a programmer, a specific tool, to load the bit file into the SRAM, volatile, or to flash this bit stream to SPI flash, non-volatile, and able to reload at each power cycle. Okay, now we have seen basic. Here is a basic idea on how to implement this LFSR in FPGA using Amaranth. We have a specific register, the register with some value content at the time t. And we have a tap. The taps is always the same. The first thing is to use the taps as a mask using AND. AND through stable show the output is 1 only if both input is 1. The output is 0 otherwise. This bit AND is used as a mask, and it's for one output, for example this one, the result is the AND between this one and this one. The output may be 0 or 1 only if in a tap the bit is equal to 1. This first result here is used as an input of a reduction XOR. A XOR has output equal to 1 if and only if one of the input is equal to 1. If both are equal to 0 or equal to 1, the output is 0. Reduction XOR is something available in Verilog and in Amaranth, is simply the XOR between the first and the second. The result is used with the third, etc. And at the end, we have only one bit. So, to produce the reg at the time t plus 1, we keep highest bit, or we drop the least significant bit, we move this by 1, and we concatenate with the result of the previous operation. The interesting thing with this approach is if the taps is fixed as a synthesis time, Amaranth and synthesize tool do some pre-processing task as GCC and drop everything to keep only this bit, because this and this are equal to 1, this and this, because this one and this one is equal to 1, another, so there is only 4 bits used, and this is not required. And consequently, it's possible to improve or to simplify, because this has no interest, this has no interest, this is interesting. So this one, and this one are keep. And in fact, according to the hardware and the FPGA, it's possible to use a LUT with 4 inputs to do the same operation as this, with more complex XOR through stable.
Now that you know a little more about linear feedback shift registers and Amaranth coding methods, we are going to see a small implementation of linear feedback shift register. So here you see a class called Prn Generator, because that's what it's meant to do. Every Amaranth program is in the form of a class which implements the elaborate method. here we decided to put one more method, a constructor, to save some more informations and allow to create different sorts of Prn generator. For instance, if we want to change the number of bits to use inside our register, we can just specify it here as an argument. So here you see the value we are going to use, which is so the variable reg, which is a signal which contains bit length number of bits and is reset to the value seed every time we are resetting this signal. Seed has a default value of 1. And if you want to specify different taps, here you have another signal which contains also bit length number of bits and is reset to taps. Now let's look at the elaborate method. So as we told before, we are using two different clock domains, which are the combinatory domain and the synchronous domain. For the combinatory domain, we are computing the value of the bit we are inserting inside the linear feedback shift register every time we are shifting it. So here the associated bit is insert, and we defined it as something that equals the register, which is masked with the AND operator by the value of taps, and then we apply to this value a reduction XOR before making it the value of the bit we insert inside our register. We also define in the combinatory domain that the output of our Prn generator is the less significant bit, the bits of position 0 of our register. Then let's talk about the synchronous domain with the shift operation. So let's suppose the code here is as this one, and we do not have any with statement. This would mean that every clock cycle the register is shifted. How do we shift it? We consider that the last bits of this register are the values of the bits from the bit in position 1, which is the second one, up to the end of the register. This is Python syntax, and so those bits are concatenated with the insert bit we calculated before. So we use for this the cat operator, and we define the register as the concatenation of those informations. So if we do this on every clock cycle, the Prn generator will output a different bit every time we have a clock cycle that is terminated. But we like sometimes to have it being generated slower than the initial clock signal. And to do so, we define an if statement, which is not a Python if statement, it's an Amaranth one. So with the Amaranth if statement, we say that every time we are the next signal is in high state, we accept to apply this rule of shifting the register. But if we set this value to 0, this won't happen, and so the Prn generator won't move. So once you have your Prn generator, you may want to see what it looks like when you put it in action. So to do so, we can use a simulation before flashing it on the FPGA, and the simulation may look like this one. So every time we want to run the script, we create a new instance of Prn generator. Here we define that the number of bits will be 10, the taps we are going to use are 9, and the seed of the Prn generator will be 1. So it's stored in a variable called DUT for device under test, and we create a new instance of simulator which is based on the Prn generator module. And then we need to define what actions should the simulator simulate. So this action is the procedure that we call proc here, and we are just telling the computer that when we start the simulation, we just simulate a clock cycle tick. Once you simulated one, we get inside the for loop, which will be iterated 2 to the power 10 times. And so for 2 to the power 10 times, we are going to simulate a tick, raise the value of the next signal of our device, then simulate another tick, lower the value of our next signal, and then we are going to simulate 10 ticks in a row. So we expect it to do nothing, then shift the register on the next tick, so right here, then we ask it not to take into account any other tick until the next signal is raised again. And so for the 10 next ticks, it should not be shifting anything. So this is the procedure, and this is what we expect the simulation to run. And so we need then to add a clock to our simulation by saying here that the period of one clock cycle should be 1 microsecond, and we add the procedure to our simulation and we run it. So here we are specifying a few more things to make sure that the simulation is stored inside a file which will be called test.vcd. So we are going to see what the simulation looks like. So here, when we look at the current repository, let's look at what's in here. There is no test.vcd file, and when we run the script, so it's prn.py, then we have here our file which contains the simulation. And to look at what's inside of it, we need to use GTK wave. So GTK wave test.vcd, and so for the moment there is nothing in this window, but when we look at the bench, the top module corresponds to our device under test, and you see all the signals we defined earlier. There is the clock signal, there is the next signal, an interesting one should be the register, and probably the taps we are using. Also the output. Fine. So here you see with the period of 1 picosecond we do not see much, but it's no problem. We are going to zoom out, and now you see that just as we asked it to, it simulated a first tick, here a clock cycle, then another one, and by the moment we started the second clock cycle, the next value is now 1 for 1 clock cycle, and that triggers on the next rising edge the shift of the register. So if you want to see in a clearer way the shift of the register, maybe it's interesting to see what are the values in binary. Also this one, binary. So here you see that the taps we use are the bit in the first and fourth position. We make every time a XOR operation between all the bits of the position 1 and 4. Here we have 1 XOR 0, which equals 1, and that's why the value inserted here is 1. But if we look at later, 0 and the first position 0, so 0 XOR 0 equals 0, and the register is shifted, so we see that the 1 isn't in the same position. If we scroll, we can look at different states. Every time you see a rising edge for the Prn next signal, you see that afterwards, on the next clock cycle, there is a shift in the value of our register, and every time the one is just shifted right. Here you see 1 XOR 0 equals 1, so the bit inserted next is 1, and you see it continue to shift. So that's exactly what we expected. We also want to check if the correlation properties are verified for our signal, and so we are going to dump this data inside a file. But we want to see just the Prn sequence, and so we need to implement it also in Python. So the reduction XOR doesn't exist. We are just going to create a Python version of the linear feedback shift register. So we need a reduction XOR function, and we need a next state. So in fact, what we used as a register before, for now in the Python method, it will just be a number, which we changed the value following the algorithm that we described earlier. So it implies the reduction XOR between the taps we use and the current state of the linear feedback shift register, and then this is the operation of concatenation bitwise. Once we define this next state function, we use it to write inside a file. We write it to 2 bytes so that another program can read it, and we are done with the generation of our Prn.
Now that the FPGA has been able to generate the supposedly pseudorandom sequence, we wish to assess whether indeed statistical properties of these sequences are met. So when Nathan and Gwen implemented their pseudorandom sequence generator, they introduced this function here that allows for calling the function, the Prn Generator, and write to a file as a byte sequence the data that had been generated by the FPGA. And the beauty of this approach is that this file here that has been resulting from the synthesis can be readily read from, for example, MATLAB or its free open source implementation, Octave. You open the file, the binary file, and you read the 8-bit integers that have been stored in the file. Similarly, we can do this using GNU Radio. So say, for example, that we take our previous flowchart, but this time we take a file source, and this file source will be used with the data that has been generated by the FPGA. So here we have our binary file, which are a byte long. And let's say we repeat the data recording so that we can display the Fourier transform, the spectrum. Now these bytes need to be converted into floating point number. Remember that these are the various types handled by GNU Radio. So these are 8-bit integers. We need to convert them into orange or floating point representation. And to do this, we're going to search for the car to float. And this car to float is a converter here. So we've got this scaling factor, which you should be aware is inverse. So actually the input quantity will be divided by the scale to generate the float. In this particular case, the Prn output here is 0 or 1, meaning that we meet the requirement of GNU Radio of generating floating point numbers between -1 and 1. So in this case, we can just keep the scale at 1 and feed this time our throttle block with the output. Of course, we need to disable our previous sequence over here. And now we've got the ability to display the spectrum of the data that have been generated by the FPGA. Surely enough, from this we have a DC spike because we did not remove the DC component because we've got 0 or 1, so there is an offset. But apart from the DC spike, we see the flat spectrum, meaning that indeed the pattern has not repeated and we do have this pseudorandom sequence. Now, another property of pseudorandom sequences is that their correlation only is non-null if we find the same property. And remember that the correlation is closely related to the spectral properties. So if we have a quick look at the basics of what a correlation is, if you consider your correlation, cross-correlation between two quantities x and y, we try to find a matching pattern between x and y. So we take actually the quantity x, which is, for example, the noisy signal that was recorded, and we try to find some time-shifted copy of the pattern shifted by a delay tau. And how can you try to find if these two patterns match? Well, you try to integrate the energy over a given duration, and if this energy accumulates, then you have a correlation peak. So how do you accumulate energy? You take integrals. So by integrating over time the signal that was recorded x of t with the pattern y of t plus tau, you will have an estimate of how closely these two patterns resemble each other. Now, this is a very complex calculation because you see here that if I take the discretized, discrete time version of this calculation, it means I'm going to calculate the sum of x at time n with y at time n plus k, and that will be the cross correlation between x and y at offset time k. So this would be your discrete time correlation. This means that we need to make, if we have an n element vector, we need to make a sum from n terms which are each a multiplication, so that's n multiplication over here. And we need to do this n times, because k here will be something from 0 to n minus 1. So we need to do n times n. So this is a complexity of n squared. And this is a heavy burden on a computer. So the classical approach for implementing correlation is to consider the convolution theorem. And if you remember what a convolution is, the convolution between two quantity x and y is the integral, quite similar to this expression here, of x of t, y of tau minus t dt. And between a convolution and a correlation, we see that the only difference is that here we have a sum of a time, here we have a difference of a time. Now, the property of a convolution is that the Fourier transform of a convolution between x and y is the Fourier transform of x times the Fourier transform of y. And this is very efficient because this Fourier transform is computed through the fast Fourier transform, the FFT, and the FFT is an algorithm which uses at best the symmetry properties of the trigonometric functions, and this is complexity of n log n. So since Gauss, we know that whenever we do a calculation of a Fourier transform, we need to do it as a fast Fourier transform with its much better efficiency than the n squared. So actually, when we want to do a correlation, we're going to say that the correlation between x and y is the inverse Fourier transform of the Fourier transform of x times the Fourier transform of y, but we only need now to reverse the time, because here we had a negative time tau, here we have a positive time tau, and the complex conjugate will take care of reverting time, because exponential omega t complex conjugate is exponential minus omega t. So at the end of the day, what we're going to do is calculate a correlation as the inverse Fourier transform of a product of the Fourier transforms. So how do we do this? Well, we're going to run this through GNU Radio, and to do this with GNU Radio, we're going to create a Fourier transform, and that's you taking the FFT block here. Now, the FFT block requires that you feed it not with a stream, these are continuous streams, but we need to feed it with a vector. Actually, we need to accumulate enough data that we are going to calculate this this Fourier transform. So let's say we want n elements, and we're going to have some windowing, so we have the same n, and I like to create a variable holding this n quantity here so that we can easily change the Fourier transform size. So say we have 2048 element Fourier transform. So what we need to do actually is to convert this data stream, continuous data stream, into vectors. So how do we make a vector? We take stream to vector, and stream to vector is over here. Now these are all floating point number. These are all handling complex quantities. So say we want a floating point input. We want to have a floating point vector, and this guy over here will take n element, because if I just try to connect this like this, I'll have an issue because the length of the vectors are not consistent. So we need to replace the number of items to n, and we've created here the right Fourier transform. So if we want to search for existing repeated pattern in our signal, we wish to have the autocorrelation. The autocorrelation is the self-similarity of the data, and so what we can do is actually take this block over here, and the autocorrelation will be the result of feeding these two data blocks with the same data stream. So here we take the same data stream and we multiply conjugate to take the correlation. So we multiply conjugate over here, put it upside down, and this multiply conjugate operates on the n elements that we just created. So we take these two guys over here, we take this guy over here, and here we've got our various correlations that are going to be calculated. So if we wish now to conclude the calculation, we're going to take the inverse FFT, and actually if you wish to have the 0 time delay at the center and half the Nyquist frequency on the sides, what we're going to do is actually we're going to do it upside down. We're going to first take the reverse Fourier transform, and once we finished doing the calculation, we take the forward Fourier transform. It's somewhat the same. Forward and reverse Fourier transform is just a matter of convention between exponential j omega t and minus j omega t. Once we've created the inverse Fourier transform, we return back from stream to vector. And once we've got, so upside down vector to stream, and this is what we can send to a time sink. So we're going to take magnitude, actually we can do it upside down like this. So we take the magnitude over the n elements again over here, and once we've created these guys, we take the n input items as floating point numbers to create the time domain, and this can be plotted as the n elements of the magnitude. So here is the full chart of our correlation calculation. So if we run this, you see here that there is no repeated pattern. There is only one peak here, which is the autocorrelation at 0 delay, and there is no repeated pattern. Now we can try to see whether the pattern repeats after the length of the data. So if we try to take this a bit longer, and if we auto-scale, surely enough, we see here that whenever the pattern repeats, because it's only a 10-bit long pseudo-random sequence, if we take a longer Fourier transform, so if we take the autocorrelation over a long enough duration as the file is repeatedly read, we see here that we have a repeated pattern. Now, the correlation sequence is, this validates the fact that we have indeed generated in our FPGA a pseudo-random sequence. Now, say we want to go back to our previous LFSR source. So let's comment this guy out over here, and let's go back to our pseudo-random sequence over here. And the reason why I kept these two Fourier transforms separate here is I would like to try to see what's happening if we have two LFSR source. So remember, the two possible tap positions were 48 and 60 if I take my previous slide from before. And we've seen earlier that these are two non-repeating patterns. So if I now wish to try to compare these two guys over here, I can feed one sequence on one side and I can feed the second sequence on the other side here. And if these two patterns match, I should have a non-null correlation. If they don't match, I should have no correlation. So at this point, I selected two different patterns, and this correlation here will not accumulate coherently. You have something like 2 to the 6 over here. If, say, now I go to the same sequence on both sides, and I run the correlation again, these are only 7-bit long, so this will repeat a bit more often. But here you have something that is 6 to the 6, and this is every time the two patterns are repeated, so whenever they match. So here you have the demonstration that if you transmit a CDMA code, you can identify which is the speaker by selecting the appropriate local copy. If you have a different copy of a pseudorandom sequence, then the energy will not accumulate coherently, and you will not be able to detect the signal from the speaker. Here is the different patterns from the two sides. So now that we're finished with the analysis of the baseband signal, and that we're convinced of the capability of GNU Radio of computing a correlation through the product of a Fourier transform, as we've just done right now, we've linked the radio frequency signal synthesis from the FPGA into GNU Radio, and now we wish to go to the next step, namely modulation and transposing the signal to the radio frequency band. So we need to do two things in the FPGA to achieve this result. On the one hand, we need to find a way of generating the numerically controlled oscillator, so the NCO, which will act as a local oscillator at several tens to 100 megahertz. And we need to implement the information on this carrier. So what we're going to do is we're going to start with the most simple modulation scheme that can be implemented in the digital world, and that is binary phase shift keying. Again, that's the same modulation scheme as used on GPS, developed in the 60s and 70s, so you can see that that was kind of a convenient way of doing things, and yet it's a very efficient way of modulating, because by acting on the phase, we have the most efficient modulation scheme. So binary phase shift keying, Bpsk, is based on the idea that we transmit a carrier frequency, a sine wave, and this carrier frequency needs to carry some sort of information. And an easy way of implementing phase modulation is to say this carrier frequency will be phase shifted. So sometimes we change a phase. So in this case, for example, we're going to change over here a phase with opposite shape. And for example, at some point, we restart taking the same phase as before. So we can represent this as 0. This will be a pi phase. This will be a 0 phase. And you see here that I can define 0 as being the bit state 0, pi as being the bit state 1, or 0 again. And so by changing the phase 0 or pi, so by flipping the phase of the carrier frequency, we're going to transmit the information. So let's see how this can be implemented in the FPGA, and once the implementation will be completed, we'll try to see how we can demodulate this information using GNU Radio and a B210 software-defined radio receiver.
So now that we made sure the Prn we generate has good correlation property, we can take a look at the mixer program, which allows us to modulate a carrier signal with our Prn. So just like the Prn, this is a class which contains an elaborate method. This elaborate method contains all the calculation we need to do, and there is also a constructor to save some informations when we want to create another mixer module. So it has the same informations, the bit length, the taps and the seed, and also a frequency. This frequency should be will be used as the frequency of the Prn generation. Remember the next signal we used here? Well, based on the current frequency of the FPGA, we will generate a new signal with a frequency 2.5 MHz, just like here, to generate Prn at a certain rate. So let's look at the elaborate method. First, we want to use a clock which is not the internal clock of the FPGA, because it is not that easy to modify, and we want to create a signal of 70 MHz for the carrier, and to reach this frequency exactly, we need to use an external source, an external clock. So we defined it here, and we use a PLL to multiply its signal. We choose different factors for the frequency we generate to be exactly the one we want, based on the fact the external clock we are using is 20 MHz. And so in order to choose these numbers, you need to refer the datasheet of the PLL you want to use. And here we see that the PLL we want to use has a minimum value of the VCO of 800. So if we want to generate a 70 MHz signal, we need to find a frequency that is higher than 800 MHz and smaller than 1600 MHz. So the value we chose were 42 for the multiplication and 3 for the division, in order to reach a 280 MHz signal. And with this 280 MHz signal, which is then created through all this block of code, we will be able to generate our 70 MHz signal. So once all of this is done, we can also think about the pins we wish to use to output the information we will need. So we will need to output the carrier signal and also maybe the Prn sequence, just to make sure it is correctly done. So here is how you define some different pins on the board we use. It depends on the board you wish to use. This is how it works for the Z board. Here is the configuration file we use for the Z board, and so when we are writing here that we are using pins number 1 on connector B here with the direction of output. The 1 here refers to the fact the second connector, the BP mod, has a first output here. So this is how you refer to the different outputs and inputs through Amaranth. So we do the same for several other pins. We hope to use them to output the data to check if it's right or not. And you can also use it to define input signals, such as, for example, the clock, which is an input signal. Here we use the pin AA9. So here AA9 refers to this one, which means we could also have referenced it with the same method as here, by creating a subsignal and writing here that this is the fourth one on the AP mod connector. We also need to use our Prn Generator, which we will call here. We use the same parameters as the one we defined previously, so the bitlen argument, the taps argument, and the seed, in case we decide to change them. This one here is useless. We also define a Prn tick, which will be a signal generated by another module that I'll describe just after, So we expect this module to have an output of a certain frequency, which will be 2.5 megahertz, and this one will be used to shift the LFSR. And then we need a carrier signal, which will be generated exactly the same way as the PRN tick. So what does it look like? The PRN tick will be created with another Amaranth module, which needs two arguments, a frequency input and a frequency output. The frequency input will be the FPGA frequency, and the freakout parameter here is the frequency we wish to recreate. How does it work? Well, it's just a counter. It's a value, a signal, which can hold values from 0 to the value of the number of the amount of time we wish to wait. So this amount of time is just the frequency input divided by the frequency output. It gives us the period, it gives us not the period, it gives us the number of ticks of, it gives the frequency input and the frequency output are used to compute how many times we need to see a clock signal rising edge before outputting a different frequency input and frequency output are used to compute how many rising edge, how many clock rising edge we need to wait before changing the output of this module. And by changing the output of this module every X rising edge clock, every 8 the frequency input and the frequency output are used here to compute how many times we need to see a rising edge for the FPGA clock before changing the output of our prescaler. And so this way we just count from 1 to, I don't know, 800, and by counting up to 800, every time we reach the value 799, the counter, every time the counter reaches this value, the output will be set to 1 instead of 0. So that's how you write a multiplexer with Amaranth. And so by doing this, we are able to generate a signal with an impulse every certain amount of time. So we use it to generate the tick of our Prn generator, and we also use it to generate the carrier signal. So if we generate a pulse with a frequency of 140 megahertz, then to create a carrier signal, we need to wait every tick of this prescaler to change the output, to change the value of the carrier signal here. And by changing the carrier signal every time this output is at 1, we recreate a 17 megahertz signal. So that's how you create the carrier. And an interesting thing is that to generate a modulated signal, we use the carrier and we use the Prn generator output. By using the XOR operator, we are able to reverse the phase of the modulated signal. So let's look at how it should look like. Every time we have a 1, if we make a XOR operation, here for the carrier signal, having a 1 XOR 1 equals 0, that's how you get here the low state. And by having a 0 XOR high state, it equals the higher state, and so you get a 1, then a 0, then a 1, and this operation reverses the state of the signal. So here is what it looks like when you use your prescaler. Here it's an example of So this is how you will recreate the modulated signal, and then you write it on the different pins of the FPGA to take a look at it. Once you flash this program, if you have at disposal an oscilloscope, maybe you can use it and plug it on your FPGA board to look at the signal here in the pin B1. And so we are going to look at what it looks like when you are outputting this data on an oscilloscope. So here is the board we use.
So now let's look at the oscilloscope. Here you see in orange the signal representing the PRN, and in yellow the carrier signal that's being modulated by the PRN. So let's stop running the oscilloscope to see what the signal looks like. And it seems that the orange signal, for the orange signal, the smallest amount of time you need to wait to see the PRN change is 400 nanoseconds, or in other words 2.5 megahertz frequency. So this is exactly what we are looking for, and if we look closer to the modulated signal, here we can take a measure of our carrier signal that's being modulated. Its frequency seems to be around 70 megahertz, and every time you see a change in the PRN here, the shift happens and the phase changes. So here it goes up, and instead of having a higher and lower state, you have twice the higher state and then the lower state. And here, when the PRN is going down, the phase, instead of going down then up, stays down for a period.
Okay, so now the FPGA of the Z board has been configured for generating this binary phase shift keying message over a 70 MHz carrier. So binary phase shift keying meaning that the phase of 0 or pi is encoding the symbol states -1 or 1, or the bit state 0 or 1. And so the challenge now is that these two boards, the transmitting board, which is here the Z board, the blue light indicating the FPGA is flashed, and now the data is being streamed over here on the 70 MHz carrier, 2.5 megabit per second Bpsk. And this clock of this FPGA is not the same one as the one clocking the B210 software-defined radio receiver. So this frequency offset means that despite a 70 MHz nominal frequency transmission occurs over here and is fed through this hefty set of attenuators to make sure we don't damage the input of B210. The 70 MHz nominal input is not exactly at 70 MHz on the input of this radio frequency front end over here. And this frequency offset means that there will be some phase accumulation. If we have a frequency offset of delta f, we accumulate a phase offset of 2 pi delta f times t, and this phase drift will prevent easy identification of the phase state on the binary phase shift keying transmission. So our objective here is to try to find a way of identifying and cancelling this frequency offset, and then to identify the symbols. So let's see how we're going to do this with GNU Radio. So we start with a clean sheet, and the first thing we do is we search for the USRP which represents the B210 software-defined radio receiver. We double-click to set the carrier frequency. We set an educated guess of 30 dB gain, and we go on the TX-RX input. So we have a transmission at 2.5 megabit per second, so 32 kilosample per second is well below the necessary bandwidth. Let's say we take something like 6 megahertz bandwidth, and we first try to assess the amplitude of a signal that we receive. Is the gain that we selected reasonable with respect to the attenuation that we included on the radio frequency path? So we execute this flow graph from the B210, and we see here that we have an amplitude which is about plus or minus 0.5. So we can gain a little bit to try to fully use the accessible range. Say we gain a factor of 2, so that's 36 dB over here. And if we run this, we should be using the full scale of the analog to digital converter. So surely enough, here -1 to +1, and you see the drift, so the phase drift appears with the I and Q coefficient fluctuating slowly at the rate of the frequency difference between the two speakers. So if we look in the frequency domain, if we want to have a look at the spectrum analyzer, we can see that actually the carrier at 70 megahertz has been spread by the modulation, and this spectrum spreading will occupy the full bandwidth from -2.5 to +2.5. The two notches here are at the data rate, and we've spread the energy over the whole bandwidth. So the objective of the demodulation is to try to identify the carrier, and a classical way of identifying a carrier is to square the signal. Indeed, if you have a binary phase shift keying, so with a phase of 0 or pi, by squaring the signal, we're going to create something that is, so from 0 or pi state, we're gonna square this, and by squaring argument we get something which is 0 or 2 pi, and 2 pi is 0 radians. So this means that we collapse all the energy in the carrier by doing this, and we should be able to see a clean carrier on the spectrum analyzer at twice the frequency offset, because by squaring we also double the argument of the delta f. So we have 2 times delta ft in this spectrum. And surely enough, here is the collapsed energy in the carrier. So exactly what Costas loop is doing is it will identify the frequency offset of this clean carrier over here and compensate any remaining frequency offset between the transmitter and receiver. So let's see how Costas loop is doing this. If we request a Costas loop and insert it so that we can easily feed the time sink, Costas loop is giving you the information in the documentation. You need something like 2 pi over 100, and this bandwidth, and this order is actually, that's not completely obvious from the description, it's the n in Npsk, so Bpsk will be 2, Qpsk will be 4, and so on. So in our case we have a loop bandwidth of 2 pi over 100, and the loop is 2 because we have a Bpsk. Now the Costas loop really likes to have a constant amplitude signal to work properly. So what we need to do is wise to include an automatic gain control before the Costas loop to make sure that it's fed a unity gain, unity amplitude signal. So here we aim at giving an amplitude of 1, and if we look at the oscilloscope, we have a 2-input oscilloscope now, where we're going to feed the Costas loop output at the same time as the time sink. And what you're going to see now is that thanks to the Costas loop frequency correction, these two guys here are still oscillating widely due to the frequency offset. But if you look after Costas loop correction, you see here that the actually, if we auto gain, if you see here that now the imaginary component has been cancelled and only the real part is fluctuating, because cosine of 0 is 1, cosine of pi is -1, and sine of 0 or pi is 0. So here we have a proper lock of the Costas loop. So now that we've identified this, we can look in the constellation sync what this means in terms of constellation. We can have the constellation displaying what is happening after the Costas loop, and just to see what it means that there is a frequency offset, because 2 pi ft means that the constellation will constantly rotate, we expect to have a rotating constellation and to have a fixed constellation. So what do these constellations tell us? This is a constellation prior to Costas loop, and this is the constellation after Costas loop. So here we see that the frequency offset has been cancelled, and surely enough we've got these two states at -1 and +1. However, you still have all these lines connecting the two bit states, and that's because if we look here at the possible phase states, we have not only the stable states at ±1, but we also have all the transitions. So we need to lock not only on the carrier, but we also need to lock on the bit rate, and this is taken care of by the symbol synchronizer. So symbol sync over here, which is so let's get rid of a few of these guys over here. Now we're convinced over here, and if we now look at what the symbol synchronization is doing, it will take an algorithm. Here's Müller and Müller. It expects a known sampler per symbol, and these are the loop bandwidth that will try to correct for any offset between the sampling clock and the expected clock. So the sample per second is defined as a variable, and this variable of SPS over here is actually the sample rate, so samp rate, divided by the data rate. In our case, it's 2.5 to the 6 megasample per second. So let's see what's happening if we feed the output of a Costas loop and we look at the output of the symbol synchronization on a constellation sync. So here we can check what is happening on the binary phase shift key modulated signal after compensation of a frequency offset and synchronization. And nicely enough, here are the two symbols that are well separated. So now you can go from the soft bit state with fluctuating amplitude to a hard bit with a threshold around 0 here. The imaginary part doesn't carry any information, and all the information is carried on the real part. So here you have the full demodulation with your two bit states. So this is summarized over here: automatic gain control, squaring to recover to demonstrate the carrier recovery, Costas loop for compensating for frequency offset, and symbol synchronization. All these constellations showing how we can compensate for inaccuracies between the two speakers. Now, we just mentioned that in Bpsk only half of information is used because we're sending all the information on the I channel and nothing on the Q channel, which is a waste of bandwidth because we've got two orthogonal dimensions, imaginary and real part of the signal. So what we can do is actually try to modulate both quantities I and Q, so the two quantities representing the complex number that is being transmitted. And if we Bpsk modulate I and Q, so we take the real part being 0 or a -1 or +1, or the imaginary part as being -1 or +1, we end up having 4 bit states. The 4 states are a phase of 0, pi over 2, pi, or 3 pi over 2, which represent these 4 positions in the complex plane. And this means that every clock cycle we're sending 2 bits because we have 4 possible states, so that's 2 bits at every clock. Actually, nicely enough, the spectrum occupation of both Bpsk and QPSK techniques will be the same, and yet we're going to send twice as many data through this radio frequency channel. So for a given analog bandwidth, we're going to send twice as many data. So let's see how QPSK is practically implemented in Amaranth on the FPGA. Back to you, Nathan.
Now that we are getting interested into making a QPSK signal, a QPSK modulation, let's look at the Amaranth implementation. So here, just as usual, the Prn Generator. We start from here every time. The parameters that are here, that are used here to prepare the register and the output. And you see now that we are preparing a second output, because when we are modulating with QPSK, we do not need only to modulate one carrier signal, but in fact 2 carrier signals that are supposed to be in quadrature. So here we have the PRN output that is supposed to modulate the identity signal, and here the quadrature signal. So there is not so many changes here, except the fact that now, instead of only using the last bit of our linear feedback shift register, we are going to use two of them. So we use the two last, and to make sure we are not still doing Bpsk modulation, we also need to think about the fact every time we are shifting our linear feedback shift register, we do not need only to shift it once, but twice. And in order to do so, we have the self.next signal, which is usual, and we have a next2 signal, which will take the value of next. We add this rule in the synchronous domain in order that when the next one signal is going down, we still remember that the signal was up in the last clock cycle, and so the condition for us to shift the linear feedback shift register is that either the next signal or the next two signals are at their high state. So for the prescaler, there is nothing to say more than what we did last time. And for the mixer signal here, let's start it again from the beginning. Instead of having only one carrier, we have a carrier with a 0 phase shift, a carrier with a 90 degrees phase shift. We have then two modulated signals, which we are going to mix up in the end, and the same usual characteristics. Here I made a few changes to allow us to run a simulation before looking at the signal on the oscilloscope. And so we can specify that if we are trying to run our Amaranth algorithm while connected to a board, we are doing what we did the last time, and if we are not doing it, then for the simulation we prepare the values we should have calculated when we used the Z-board characteristics. So here we can just forget about all these parts, which is the same as before, and the algorithm restarts here. So here, just as usual, we use our Prn Generator, which this time is not only outputting one value but two. We need a Prn tick, which will be used just as before, with a frequency of 2.5 MHz. And now you see that instead of having a carrier tick, which is equal to a prescaler with twice the frequency we wish to use for a carrier, instead we are going to use another system. So you see here that the frequency is 280 MHz. This is the supposed value of our FPGA frequency. We had the rule that the Prn Generator next signal is equal to the value of the output of this prescaler here, so 2.5 MHz. And then for the carrier, we add a carrier selector. The idea here is to modulate two signals that are in quadrature, but to create them we need to have first a signal that is 4 times the frequency we wish to use. 4 times because we are going to change either the carrier with a 0 phase shift or the carrier with a 90 degrees phase shift. And to choose which one to change value of, we need a carrier selector. If the carrier selector is changing states every time we have a clock tick, by just changing the states, that makes us a signal which frequency is equal to half the original frequency. So we create a 140 MHz signal, and this 140 MHz signal, when it is in a high state, we are changing the value of this the first carrier, and when it is at lower state, it changes the value of the other carrier. So by doing this, we are dividing by 4 the frequency of each carrier, and it gives us 2 signals that are in quadrature because we are not changing their value at the same time, and they are each 70 megahertz signals. So here is just a little simulation I did to make you look at what the signals look like. So here we instantiate our mixer, we make it a simulation, and we are just simulating 1,000 ticks. So what's happening within 1,000 clock ticks? Let's look at this. We get this signal. So here is our clock. Here we have the first signal we wish to modulate. The modulation we get once we apply the first PRN output, and the second carrier, and the result you get when you modulate it too. So here you see that the PRN outputs are different, which means we correctly did our job of creating 2 different pseudo-random noise. And you see here that the carrier is being modulated by the PRN. So you may ask, what's happening? Why do we have here a high state and here a high state too, which makes a XOR? So XOR high equals normally low state. But here, remember that the rule we created here is a synchronous rule. So in fact, the operation only applies for the next tick, which is at the end of the higher state here. So here, the modulation that we apply during this state is only seen in here. And so that's why you see a reverse. Here, every time you see the PRN going from up to down state, you see a phase shift here, and you should be able to see another phase shift every time you have a higher or a lower state. So here it's interesting to remark that we see also a phase shift for the modulated signal, but this tick is related to the fact that when we are defining the PRN output, we are defining it in the combinatory domain. So every change that is happening is seen right away, and the shift you see on the linear feedback shift register here is not just one shift but twice. We shifted twice, and so there is a very small amount of time during which the second value is the one that should be seen, in fact, as the first value here for the PRN. So what we see here is just the transition that should be happening for this state here. We are quite happy with this now. Maybe we can look at what it looks like when we are running it on the FPGA. So when we are flashing it on a platform and not in a simulation, we should see in D4 both modulated signals, which are mixed together with an AND operator, and we should see in B1 the output of the first PRN, and in B2 the output of the second one. So let's flash it. Okay, so now that the program is flashed, and on the oscilloscope we see something that is really interesting. It's here you see the PRN output signal, so this is the first one, but we could have taken the second one, and here you see the modulated signal. So here there is a very big amount of signal changes possible around the 4 nanoseconds. So 4 nanoseconds is the period for 2.5 megahertz signals. So our PRN is still changing after every 400 nanoseconds, but There is some troubles with what we talked about earlier, the fact that we shift the signal twice, and so there is a small amount of time during which the pseudo-random number is not in a stable state. And so this is why you see on this garbage. But what's most interesting is the fact that the modulated signal here can shift up to 4 different states. So these are the 4 phases you get when you are doing QPSK modulations. And if we stop running the simulation, you see that the period is still the period you get when you have a 70 megahertz signal, but you can also see that during this lapse of time you can get 4 different states, and these are the 4 different states you get when you are doing QPSK modulation. About the fact the signal isn't in a very stable state when we shift the linear feedback shift register, this is not much a problem. It doesn't matter when you are demodulating. The signal is still clear to demodulate, and it's not a problem.
So the FPGA has now been flashed with a bitstream. Again, same view. We have here the FPGA, and we have the same issue of these 2 clocks not being the same. So now we're familiar with the issue in terms of Bpsk, but let's see what this means in terms of QPSK. So if we go back to our previous flowchart and if we just run it as it is, since it is configured for Bpsk, of course that's not going to work for QPSK, and the synchronization is not occurring, so that we see the constellation rotating constantly. The Costas loop is unable to lock. Yet you still see on the blue chart over here the exact same spectrum as before, from plus 2.5 megahertz to minus 2.5 megahertz. So in terms of analog spectral occupation, we have the same state, but we've doubled the data rate. So what we need to do now is to actually not square the signal, but we need to do it twice to put it to the 4th power, because if we take a QPSK signal at the 4th power, then we're going to cancel the spectrum spreading by the modulation, and we're going to recover the carrier. And similarly, Costas loop, if we want to compensate for the frequency offset, we need to tell the Costas loop this is an order 4 modulation, because it's this time a QPSK signal that is transmitted. And as you do this, now that you can consider actually that QPSK is 2 times Bpsk on the I and Q components, now you see here how all the energy has collapsed in the carrier. So this time the carrier will be shifted 4 times because we've taken the 4th power. And before the symbol synchronization, we see here the 4 possible bit states. So 0, 0, 1, 0, 1, 1, 1, 0. And we see here the linking points, because we don't lock exclusively on the stable states of a phase, but we also have the transitions. And again, after the symbol synchronization, we're only left with the 4 clouds. Now we have the same analog bandwidth, but you see here that the challenge of demodulating is that these 4 clouds are much closer to each other than they used to be with Bpsk. With Bpsk, we only had +1, -1, so putting a threshold at 0 would allow you to identify which bit has been transmitted. This time we have 2 thresholds for soft bit to hard bit selection, and of course, because these clouds are closer to each other, the risk of erroneous detection is higher. So this is a demonstration of QPSK doubling the data rate at the same analog bandwidth using the FPGA. So finally, now that we've completed our excursion through digital communication, well, a lot of ham radio are using the good old analog FM modulation, and we wanted to conclude this presentation by showing that you still could use the digital FPGA for generating the frequency modulation. So frequency modulation has been developed well before phase modulation, because it's much easier. It's an incoherent detection, meaning that you don't need to recover the carrier, you just need to compensate for the frequency offset. And that's classically achieved by using a phase locked loop on the receiver to compensate for the frequency offset between transmitter and receiver. Now your signal for FM communication is something like cosine of your carrier frequency plus a frequency excursion integral of the signal. Integral because the argument of a trigonometric function is a phase and the integral of a frequency is a phase. So here we get something that looks like what we want to transmit to get a frequency modulated signal with an excursion f delta. F delta will define with respect to the highest frequency of x whether we have wideband FM or narrowband FM, so that defines the correction bandwidth of the PLL. If the excursion is much smaller than the maximum frequency of a signal, then we've got narrowband FM as classically used by ham radio. If we have the excursion much bigger than the highest frequency component, we have wideband FM as used by commercial broadcast frequency modulated communication. So we consider that x of t, the data that we're transmitting, the signal that we're transmitting, is one of the spectral components of the Fourier transform of the Fourier series, and this is at FM one of the spectral components that we're considering here. Then the integral of a trigonometric function is again a trigonometric function, and we see from the integral f delta over FM, which nicely leads to this definition of narrowband FM or wideband FM. So what we're going to do now is we wish to tune the carrier frequency Fc as a function of the trigonometric function that we're transmitting over here. So this carrier frequency, the local oscillator, will be not at a fixed frequency but at a tuned frequency, changing with the signal to be transmitted. And this demonstration will allow us to see how to generate a sine wave in Amaranth and how we're going to use the description of a local oscillator to transmit this carrier frequency. So Nathan is going to show us how to transmit an FM signal using Amaranth.
Alright, let's dive into frequency modulation. As you probably already know, frequency modulation is about wanting to transmit a certain information in the form of frequency, for example, and a carrier signal. This carrier signal will change its frequency here, as you can see, periodically following the frequency of the signal that is used to modulate it. So if we change the frequency of the modulating signal, here you see that the pumpings you could see before are disappearing, and if you raise the frequency, it all changes. So how do we implement this with Amaranth? In order to implement this with Amaranth, let's first, you need to implement a numerically controlled oscillator. So here is an example of one, but before looking more precisely into the code, let's look at the small drawings I made. So to create a numerically controlled oscillator, you need to use a counter. So let's say we have an n-bit counter that counts up to the power n minus 1. And so this counter from 0 to 2 power n minus 1 will be referencing values inside the memory. And all the values inside the memory are representing, in fact, one sinusoid period. So by stepping into this counter, like for example if I go with a step of 2, after having completed a certain amount of steps, you will have represented the whole period of your sinusoid. You need to choose the step wisely in order that every time you are stepping, you are making sure that the amount of step you will make to complete the period of your sinusoid is the exact amount of time you need to represent your signal. So how do we do this with Amaranth? As usual, there is a class with an elaborate method and a constructor with some parameters. So just like for Prn, we add a tick frequency information, as we are probably going to say to our FPGA whenever we want the steps to be completed. This is why we have a tick frequency parameter. We also choose a resolution which will be of on how many bits we wish to represent the sinusoid. In that case, the sinusoid is represented by an 8-bit memory, so every value will be between 0 and 255. You also need to know what is the maximum frequency you wish to reach with your numerically controlled oscillator, because if you don't, you won't know what size should be the signal that is representing the input of your FPGA module. So here in the constructor we are instantiating a discrete version of the cosine function. So this is where we are going to store all the values. Each one of these values before we are storing them in the memory. So we are doing this in regular Python by just using the cosine function of the math library of Python, and we report all the values of our cosine function to a range between 0 and 255. Here we are defining our memory, which will be an 8-bit memory with a certain number of points that are to be saved. And you need also, once you've stored the tick frequency, here is the signal tick. You will drive with a frequency of tick frec. Here is our input frequency. We are saying here that we wish to output a signal of this resolution, and some more information are useful, such as the accumulator, which will be our counter, the size of it, a gain that you wish to apply to avoid doing some specific calculations while you are in the FPGA, and a unit. This is the smallest unit of frequency you are able to differentiate with your numerically controlled oscillator. As you can see, it depends on the input frequency, it depends on granularity you ask. If you ask a granularity of 1, it implies that you expect your unit to be 1 Hz. So this way, every time you are using your steps, the step is equal to the unit you are using multiplied by the input. If I want to create an A key, well, A is 440, so 440 times 1 Hz makes us 440 Hz. And so this is the size of the step you will need to make, so that every time your counter will overflow and go back to the value of the beginning in the beginning of your counter, every time you are creating an overflow, the amount of time you have waited relative to 440 Hz frequency. And then just as we did before, we say that every time our tick signal is in the high state, you will increase the value of your accumulator. So now we are going to test it. So this is French notation for the keys. Here you see our A with 440 Hz frequency. We expect our NCO to be driven by a frequency of 48 kHz. Here we are defining our NCO. The number of bits is 8. So this will be our resolution. And within the test, we are just copying to play a certain number of keys. Let's try this on the terminal. So you can see here the keys that are appearing one by one as they are simulated. And once they are all simulated, now we should be done. Yeah. Let's look at them. So here is the value of our accumulator. Here you see in the memory every values that are stored for the numerically controlled oscillator. The input frequency, so the frequency of the keys we wish to play. Here is the size of the step. It should change every time we are changing the input frequency. And the output. We will add a few analog height extension and change the format of the data so that we see a nice signal, a nice sinusoid. And when I'm zooming out, you start seeing the changes. I didn't change the format. And you just created a nice sinusoid. If I'm zooming out even more, we are able to see that the wavelength or signal changes while we change the input. Here, let's see in decimal. So it's around the frequency we asked for our program. And it gives us all the keys we asked for. Alright, so it's fine that we can create music now, but we wish to use it to modulate a signal. In order to do so, we need another module. So this module, my radio emitter, is much simpler in a certain way, because we do not much care about memory. Anyway, we need to instantiate a PLL just as before to have a high enough frequency so that we can have a nice resolution for the signal. So just as before, we define also the pins on which we wish to output our signals. And here we are recreating all the different aspects of our FM modulation. So first of all, we need a sampler which will give the rhythm at which we will update the value of our NCO. So you see here in the test that I used 48 kilohertz signal. And so, as our PLL is different from 48 kilohertz, we need a sampler, which is just the prescaler class we used before, to give us the right take in the right time. We recreate the baseband signal, which is just an instance of an NCO, with the sampler rate we asked the sampler to recreate, a certain resolution, and baseband width is the maximum value you can ask the NCO to recreate. And so, to create our radio band signal, well, it's just another NCO, but with a much smaller resolution. With a resolution of only 1, we will output our signal on only 1 GPIO pin, and so we can only create binary signal. But it's alright as long as it has the right frequency. And so the frequency of its input is the current frequency of our FPGA, which is calculated right here. And the maximum value you can reach with this NCO is baseband width value multiplied by the excursion. So to make the signal much clearer once you demodulate it, you choose a factor that to multiply the value you have calculated in the baseband signal plus the original value of the radio carrier. So at first we will have a 70 megahertz signal, which will be modulated by a signal within this baseband width. So here is the set of the rules. We are enabling the sampler to make sure that it is giving the tick to our NCO. We are setting to 1 the value of the tick of the second NCO, so that every time there is a clock signal, the tick here is set to 1, and so this rule will always be applied. We make the tick signal of our baseband signal equal to the sampler output, so for 48 kilohertz. We make the input of our baseband signal the input of the whole module, in order that we can modify it when we run the radio emitter from the FPGA, for example. And we define that the radio band signal input, so the frequency of this numerically controlled oscillator, should be equal to the carrier, 70 megahertz, plus the baseband signal output, which will be our nice sinusoid we created here, multiplied by the excursion to make the signal much clearer. And so here is just a little partition I wrote for a test. We define a memory to store this partition, and then we can play it with a certain tempo, which is defined just here. So a frequency of 4 Hz. If you want to look at the defined bit function, it's just here. It's just a prescaler, nothing so complicated. And so you add the last rules to make this music being played by the FPGA. So let's look at it.
And while the bitstream is synthesizing, here is a flowchart for radio decoding. We select the data rate, integer multiple of the output audio rate, and the narrowband FM receiver outputting 48 kilosamples per second.
Alright, so we open GNU Radio. So our baseband signal is 70 megahertz, and when we run this, and here we are.
Now the gate array is working on the Z board. It's interesting to see if it's possible to use another board with the same code and the same functionality. In fact, Amaranth gate array are more or less hardware independent. In fact, it's dependent of block used. There is some generic task, classic, comb, sync, etc. And there is some specific block dedicated or available only on a specific device, like a PLL. Amaranth use a platform description. This is most common or official board supported are present in GitHub on the Amaranth board repository. In this repository, there is some Xilinx or lattice board with open or closed hardware. Each of them provide all information required to build a gate array for this specific target. So we have used the Z-board based on the Xilinx Zinc device, and to build the gate array for this platform, we have used Z-board platform with a parenthesis, so this is an instance of the platform, and we have called build method by passing the instance of our gate array. The do program is used to specify to load the bit stream to the device after the end of the build. This platform provides everything required to know the toolchain and to know how to use all synthesis, map, and bitstream generation tools. To move to the Radiona ULX3S, this board, based on a different device, FPGA, a lattice ECP5, we have just to replace the Z-board platform by the ULX3S platform. This platform is officially available on the Amaranth repository with 4 flavors depending of the FPGA device. In fact, the size of the FPGA, all of them inherit from the ULX3S platform. This one describes the common part of all flavors. This means the package, the speed grade of the device, and the clock name for the default clock. The second thing provided by this class is the resources. Resources and resource are description of pin with a specific purpose. For example, this pin is the default clock and can be used for other behavior than providing the clock. It's the same for example, the LED button and UART interface of all SPI, RAM, etc., etc. There is a lot of functionalities. The second aspect and the second type of pins are provided by the connectors list and the connector. This is generic purpose pins without specific behavior functionality and user-defined use. These pins must be packed into resources and to extend platform when you need to use one of them. This GPIO are this one and this one. The last aspect of this class is the lattice ECP5 platform. It's a generic class used to provide toolchain and how to deal with this type of FPGA. So here you have our platform, but since we need to have an high frequency clock to produce the required FM frequency, we have to adapt a bit our gate array to use the correct PLL for the lattice ECP5 or the PLL for Xilinx Zinc. Our elaborate method provides a platform parameters. By using type with platform as a parameter, it's possible to compare this with the platform type. For example, it's equal to the Z-board platform. We have to use a Xilinx PLL or MMCM. Else, we use the ECP5 PLL specific block. And of course, it's possible to append this list by using another test to use with another platform.